Welcome back to this video lecture for the course ENSC112 heat transfer. And right now we are going to discuss the combined heat transfer modes. The idea is that the basic modes of heat transfer, the conduction, convection, and radiation, they can actually occur simultaneously in a given situation. And in some situations, probably only the two modes are significant, like for example conduction and convection only, and we can just disregard the radiation if it's not significant. Or probably in some problems, the significant ones are the convection and radiation. And it's also possible that all the three occurs simultaneously, and we need to take into account the effects or the contributions of both the conduction, convection, and radiation. So how do we solve that, or how do we analyze this kind of problems? Is that's what we are going to tackle in this topic. Okay, so to give you a real example of these combined heat transfer modes occurring simultaneously is, let's say we have this building, the building roof, and we know that a building is, of course, there's going to be a sun, and the sun actually radiates heat, right? So there's going to be radiation. It's right here, radiation. And there's also going to be air that's flowing over the surfaces of the building, so there's going to be convection as well. And if we try to zoom in right here, then probably we can say that, let's say here's the model for the roof material. Let's just model it as one material or a solid material. Then what if we model this radiation as going in this direction, and also the convection, let's just say it's going in this direction, right? So here's our radiation, and here's our convection, and right here there's gonna be conduction that's occurring across this material. And if there's going to be air that's moving inside, and if it is significant for analysis, then we can say that there's still going to be convection right here. All right, so that's one of the example where in these combined transfer modes they occur simultaneously. Another situation is if we have this pipe right here, and in that pipe, inside that pipe, there's going to be flowing fluid, let's say water, it's flowing inside the pipe, and outside the pipe there's going to be, or it's going to be subjected to another fluid motion, but in this case probably, let's say this is air, right? So there's going to be convection, right? Convection outside, and within this pipe material, then there's going to be conduction, and inside this hollow in this hollow portion there's going to be another convection. Okay, so if we try to take a look at section, let's say here's our section of the pipe. So outside here there's going to be convection, and inside there's going to be conduction, and inside right here there's going to be another convection. So how do we solve this problem? That's what we are going to discuss in this topic. Now, in order to be able to solve this problem, there is a concept that we'll be using for analysis, and it's called the thermal resistance. And so, we call this thermal resistance concept. And when we say resistance, it's something like it's going against, or it's something that blocks the flow, something that blocks or hinders the flow. And when we say thermal, then of course we are referring to the flow of heat. We can actually understand this thermal resistance if we talk about, or if we discuss it in terms of analogy between the fluid flow, the electric circuits, and then this heat transfer resistance. Okay, so first let's talk about the electric circuits. If this is an electrical conductor, let's say a electrical wire, then of course inside that wire, or I don't know, maybe outside that wire, depends upon how they interpret that. What I'm just trying to say right here is that for a charge to flow, and the flowing charge is what we call this electric current. Okay, electric current is the moving charges. So in order for this charge to flow from one point to another, let's say here's our point 1, here's our point 2. So in order for the charge to flow from point 1 to point 2, there must be some driving force, right? So that driving force is what we call the potential difference, or the voltage, right? So that's going to be our driving force. So there must be a voltage or a push. And as the charge is moving along this electrical conductor, it actually experiences resistance. Why? Because there is a resistance as a property of the material. Okay, so again, consider this electrical concept. So we have an electrical conductor, and in order for the charge to flow, the electric current, in order for that to occur from point 1 to point 2, there must be a driving force, and that driving force is the voltage, or the potential difference. But as the charge travels, it actually experiences resistance. Okay, why? Because of this electrical property, there is a resistance property, or electrical resistance property for or in the material. Okay, another concept is in terms of the fluids. So let's say we have a pipe, and in that pipe there's actually a moving water, or a moving fluid. So in order for that fluid to flow, there must be a driving force. Let's say here's our point 1 and here's our point 2. So what's going to be the driving force? There must be a pressure difference, right? Or let's just say pressure difference between point 1 and point 2. Okay, so in this fluid concept, in order for the fluid to flow in that pipe, there must be a driving force, and that driving force is the potential difference. But as this fluid flows inside the pipe, it actually experiences resistance, right? So resistance where, or how come there's resistance? Okay, we have resistance due to friction. So as the fluid flows in that wall surface, there's actually friction that's going on. So that's it. That's the resistance. Now the same goes true for heat transfer. Let's consider conduction heat transfer for now. Let's say we have this material, and let's say we have there is a heat flow that occurs. Right, so here's our Q, from this direction to that direction. Now, in order for the heat to occur, from point 1 to point 2, there must be a driving force. and the driving force is the temperature difference. And as the heat flows, or as the heat travels from point 1 to point 2, it actually experiences resistance. So we have here the resistance, and this is what we call the thermal resistance. Okay, thermal resistance. Okay, thermal resistance could be in terms of conduction, heat transfer. Then that's because of the thermal conductivity or property of the material. Or if in terms of convection and radiation, then that's simply because of the heat transfer coefficient, in which we will discuss later. Okay, so now you see the analogy, and if you try to plot this, if you refer to our lecture handouts, we have here the table 2-1. So we have analogy between electric circuits and, of course, fluid mechanics and heat transfer. So here's our governing, I think we'll start with this. So the driving force, the potential difference, is the voltage or the voltage drop. And the ones that's flowing is the electric current. For fluids, pressure difference, and the ones that flowing is the mass flow rate or the volumetric flow rate. This is right, flow rate. For the heat transfer, that's the heat, and of course, that's heat rate or heat flux, depending upon the given parameters. Okay, now in terms of equation, you are already familiar with this Ohm's law. The Ohm's law is V is equal to IR. It just simply says that the voltage drop or the potential difference is equal to, or is directly proportional to the current, right? By this factor. Now, if I want to rewrite this, we can rewrite this as V all over R is equal to I, right? So here's going to be our form, and this is our driving force. Here's our resistance, and here's what's flowing, right? Now in heat transfer, we can actually write that as well. We have this Q, and what's the driving force? That's going to be delta T, the temperature difference, and we have here the R, which is the thermal resistance. Right, so here's our thermal resistance. This one is heat. Okay, this is the driving force. Now in fluid mechanics, actually it's not exactly the same as the heat transfer, the electric circuits, because the flow rate, let's say the Q, that's the flow rate, and here's the driving force, the H sub F, that's the head loss or the pressure drop, or the change in pressure. So that's the pressure drop, and here's the friction. So you would notice right here that the Q term is not actually, the degree of the Q term is actually raised to 2, so that's going to be squared. It's not a linear relationship between this driving force and the friction, or the resistance. Okay, but at least you get the idea or the analogy between these three areas: the electric circuits, the fluid flows, and the heat transfer. By the way, how is this derived? It's just I think this is from the Darcy-Weisbach equation and the flow rate equation. Okay, so that's enough for that. Now let's go on to the details of the thermal resistance. Now, what if it's a conduction resistance? What's going to be the form if it's a conduction resistance, or convection or radiation resistance? Okay, so recall that the expression for the thermal resistance is simply Q is equal to delta T, the the driving force divided by the resistance. Now for conduction, this R sub K, this thermal resistance for conduction is labeled as R sub K, which is just equal to L. This is L all over K times A. What is L? That's actually the length of this, or the thickness, or what we call as delta X in our previous discussion. And the K is, right, this K is the thermal conductivity of the material, and A is the surface area, or the area that is perpendicular to the heat flow. The L is the length parallel to the heat flow. Now for the convection resistance, we have here's the temperature difference, the difference between the surface temperature and the fluid temperature, and our resistance is labeled as R sub C. R sub C is expressed as 1 all over H sub C times this AS. This is the surface area, and the H sub C is what we call the heat transfer coefficient for convection. And for radiation resistance, again, the driving force is just the change of or the difference in the temperature between the surface temperature and the temperature of the surroundings. So the difference actually between this convection and radiation is this one is based on the surroundings, whereas this one, the convection, is based on the fluid temperature. Okay, the resistance is R all over R, and this just simply expressed as 1 all over H sub R AS, where in this H sub R, that's the heat transfer coefficient for radiation. Something like this H sub C, except that this one is for radiation. And of course, the expression is given right here. How do we solve for that H sub R? We can use this expression. Now, if you notice that we use this symbol, we have these 2 points right here. Let's say point 1 and point 2, that's going to be the temperature, T1 and T2. And right here, we use this something like a sawtooth symbol, and that's our model for thermal resistance. So if the resistance is conduction, that's R sub K. If it's convection, that's R sub C. And if it's radiation, that's R sub R. Alright, then the next is the concept of thermal resistance actually becomes appreciable when solving one-dimensional problems with combined heat transfer modes. Okay, so again, this concept of thermal resistance becomes appreciable when solving one-dimensional, meaning that the heat flow is only along one direction. Let's say along the X only, or along the Y, or along the Z. As long as it is one-dimensional, we can use this thermal resistance, and of course, it should be noted that this is, I think, only for steady-state problems and without heat generations. Okay, so for now, let's just consider the basic problems regarding this combined modes of heat transfer. Okay, one problem is the composite wall section. So right here, we have a composite wall section. So in other words, that we have, let's say, 3 materials in series in a given wall. Let's say a wall of a cold storage, or a cold room, or refrigeration applications, wherein you don't want to pass the heat from the inside to the outside. Okay, so in that way, you need to do some composite wall sections. Okay, so if you see right here, we can actually model the thermal resistances in series. Let's say here's our material A, here's our B and C. So each material will have, let's say, different thermal conductivities, and therefore there will be different R sub A. There'll be different resistance at A, at B, and at C. And of course, there's gonna be changes in the temperature. Let's say temperature at 1 or temperature at 2 or 3 or 4. And it's also possible that we have these composite wall sections in parallel. So in other words, the illustration for the thermal resistance network could be something like this. Okay, so how do we solve for this? Let's say we want to solve for the total heat flow for a series, then we just need to sum this up, add these resistances, and then convert that to total. And if it is in series, then the R total is just simply R sub A plus R sub B plus R sub C. But if it is in parallel, we will use this expression. Okay, because as heat moves from let's say from this point to the wall, then since we have two materials, then it will split something like this. So that's gonna be Q at A and then Q at B, and then it will the total heat, which is simply the sum of the two. Alright, so that's one problem wherein we can use this thermal resistance concept and we have a composite wall sections. Now another problem is if we have conduction and convection in series. In actual situations, the example here is the heat exchanger or the building walls wherein the outside surface is exposed to some moving fluids or moving air. So we have conduction and convection in series. So how do we model that? We can actually model that using this series concept. So let's say we have a multiple wall section and we need to take into account the convection at one surface and another surface. So how do we model that? They're actually in series. So from the temperature of the fluid to the surface temperature, 0.1, then we have this resistance. But the resistance is R sub C. That's the convection resistance. Now from 0.1 to 0.2, we have another resistance, but that's the conduction resistance. From 0.2 to 0.3, this is another resistance, but in conduction. And from 0.3 to the fluid temperature right here, then that's going to be another convection resistance. Okay, so if we can just sum this up, then that's going to be the R total, and then the driving force or the potential difference or the temperature difference from this point to that point, and we can get the total flow, total heat flow. Okay, next problem is this combined heat transfer coefficient. Okay, so a surface exposed to the surrounding air involves convection and radiation simultaneously, and the total heat transfer at the surface is determined by adding or subtracting if it is in opposite direction, the radiation and convection. So right here in figure 2-3, so here's our surface. So here's our surface, and right here we have actually when the temperature of the surroundings is approximately equal to the temperature of the fluid, then we can actually apply this concept. So here's the temperature of the wall, right? So here's the temperature of the wall and here's the temperature of the fluid, and let's say they're just equal or approximately the same, then it is said that if convection and radiation occurs, then they are modeled as parallel networks. Okay, and in terms of the flowing medium or the flow, it's gonna be simply this total flow is just being split up. One heat flow or a portion of heat flow would be contributed to the radiation, and another portion of heat flow would be contributed to the convection heat transfer. So that's why we have this relationship. Now, how to solve this R sub R or R sub C? Then we'll use the we will use the um, recall that R sub R is equal to 1 all over HR times AS, or if we are solving for heat flux, or if this is not given, then you don't need to include that. Then just work through the units. Now for R sub C, this is 1 over H sub C. Again, if this surface area is not given, I mean if we're solving for heat flux, then we don't need that. Okay, so for the combined heat convection and radiation, we can actually use this equation. This is a simplification. H combined is equal to H sub C plus H sub R. And then just take note that if you have a problem of combined convection and radiation, it's actually a convection equation. Here's the equation that the total heat flow is just simply the combined. So you notice that this form, this is a convection form. Except that the H combined is just we'll take into account the radiation coefficient, I mean heat transfer coefficient by radiation and heat transfer coefficient by convection. Okay, and lastly, I'll just would like to bring up this topic, but about this overall heat transfer coefficient. But the idea actually is this: the overall heat transfer coefficient. This is just simply the U. Okay, and the U is just actually equal to 1 all over RT. So let's erase that A. So U is just simply the reciprocal of this R, of this total resistance. Okay, so why is that? There are other symbols like this overall transfer coefficients, just simply because some applications will have already this value, this U value for the materials, or for the combined materials or composite materials. So at least it's very handy already. Alright, so now in the next video we will start doing sample problems regarding this thermal resistance concepts and how to use that. Okay, so see you in the next video.